What we're going to explain in this video is the process of making of cocaine, which is a naturally occurring substance. Yes, cocaine is not manufactured inside a factory, for example, or anything like that. It's all made naturally inside of a plant, which makes actually this more magnificent because every single step you see doesn't have any form of human intervention. It's all made of inside of a plant called coca plant. So just to start, cocaine comes from a plant called coca plant. Cocaine, coca, makes sense. The scientific name of this plant is Erythroxylum coca, which comes from a family named Erythroxylaceae. Every single plant actually has a family that it belongs to. It's a form of classification of every single organism that's on Earth. So the family is called Erythroxylaceae, and the genus and species of the cocaine itself, the scientific name of the plant is Erythroxylum coca, which is mostly found in South America. I was about to say South Africa. And another very important thing, since we're discussing the chemistry, it belongs to a group of chemicals called tryptane alkaloids. What is alkaloids and what is tryptane? That's a very valid question, and you have the right to ask that question. Alkaloids are a form of chemicals that are extracted by humans from plants. They could have very beneficial medicinal uses as a drug, or actually could be poisonous with some uses for some people. These are alkaloids, and what do they have in common to make them categorized as one thing is a nitrogen atom in their structure. This is what all alkaloids have. There are certain classifications for alkaloids, including tryptane alkaloids, and tryptane alkaloids are the alkaloids that have all of this skeleton inside of them. This skeleton actually is called a tryptane skeleton. So tryptane alkaloids are alkaloids that do have a nitrogen atom. All alkaloids have a nitrogen atom inside of them, and tryptane alkaloids are the alkaloids that do have all of the skeleton, like this bicyclic skeleton inside of them. That's the tryptane alkaloids, and the most famous tryptane alkaloid out of all the tryptane alkaloids is cocaine, for example. The starting material that we have is L-glutamic acid. L comes from the stereochemistry of this. If you don't know what is stereochemistry basically explains the spatial orientation of a certain molecule in space. You know, compounds are not planar, as you know the structure. It's not just something that's very straight on a planar object or on a paper like that. It's bent. It has a certain spatial orientation in space because it's three-dimensional, right? So this L, which means levorotatory, explains a certain orientation of this L-glutamic acid in space. And it's abbreviated L-glu, and it refers to L-glutamic acid, which is an amino acid. Amino acid is lots of amino acids form proteins, as you probably know that. All right, so we have L-glutamic acid. This is the structure of L-glutamic acid. What we're going to do is we're going to add an acyl group to it. This is called an acyl group. We're going to add this in here, and we're going to remove one hydrogen, to add it on the end, and then we're going to call this structure N-acetyl glutamate. Why N-acetyl? Because we added the acetyl group on the nitrogen. So the name is going to be N-acetyl glutamate, still glutamate, because it's exactly the same structure. What just happens is that we added an acetyl group on the nitrogen, and then we named it N-acetyl glutamate without any change in the main glutamic acid. This happened by the help of an enzyme called N-acetyl glutamate synthase. If you actually try to understand the name of the enzyme, it makes a lot of sense. N-acetyl glutamate synthase. Synthase comes from synthesis. We made N-acetyl glutamate, so the enzyme that helps in this is called N-acetyl glutamate synthase. We're gonna write it in here. It's the exact same name of the compound, but just with the addition of synthase. All right, so then we have the N-acetyl glutamate. What we're going to do, we're going to make N-acetyl glutamate 5-phosphate. We're going to add a phosphate group on here, on this carbon. All right, this is another intermediate in the process that we're doing in the making of cocaine. So the enzyme that helped us in the making of this is called N-acetyl glutamate kinase. Actually, this is a very important biochemistry. This is a very important biochemistry tip. Whenever you hear the word kinase, immediately know that you added the phosphate group. You made a phosphorylation process. So a kinase means that you phosphorylated this structure. So this means that you added the phosphate group in here. So this is the structure we have right now, N-acetylglutamate 5-phosphate, and then it's going to transfer to N-acetylglutamate semialdehyde. What had changed here? We removed this one, and then we added a hydrogen in here. Instead of the OH that we used to have in here, we reduced it to a semialdehyde in here to be N-acetylglutamate semialdehyde. And the enzyme actually that was used in here is an enzyme called dehydrogenase. So this is the whole process. By using N-acetylglutamate semialdehyde dehydrogenase, we made a compound called N-acetylglutamate semialdehyde. All right. This is the aldehyde group, by the way. This is called an aldehyde group. What's next? We made something called N-acetylornithine. N-acetylornithine is basically the same structure, but instead of this aldehyde group that was in here, we removed it, and then we added an amino group in here. This process happened by the help of an enzyme called N-acetylornithinase, because we made N-acetylornithine by it. So it's the same name as this, but with an enzyme called ornithinase. We made this whole structure. What's next? We've reached a very main compound in the process of making cocaine. Actually, I forgot to tell you that on the top of this board, I made you a list of the main compounds that are essential in the making of cocaine. First of all, we started with something called, as we've mentioned, L-glutamic acid. We're done with this. And then we reached ornithine. Everything that's written in pink is essential in the process. The second one is ornithine. Now we've reached ornithine. What is the other essential one that we need to reach after ornithine? Is a compound called putrescine. What is the difference between putrescine and ornithine? The difference between putrescine and ornithine, actually I forgot to mention first, how did we change N-acetylornithine to ornithine? Nothing. We just removed the acetyl group that was found in here. This is an acetyl group. We just removed it, and then we have this structure without the acetyl group that's found in here. That's how we made ornithine. So how did we change ornithine to putrescine? We changed ornithine to putrescine by removing the acetyl group that's found in here as well. Two consecutive steps that were made by just moving the acetyl groups. All right. Actually, you could say that it's somehow, but this is not an acetyl group. It's mainly a carbonene atom. But you could say that 3 carbonene atoms were removed consecutively in 3 consecutive steps. All right, until you made putrescine that has no carbonene atoms or acetyl groups. So this is removed, and then we have putrescine. All right. So the enzyme that was involved in here is ornithine. Yes. Or no, not ornithine actually. No, it's ornithine decarboxylase. Yes, it makes sense. Decarboxylase. Decarboxylase because you remove the carboxylic group that is found in here. Acetyl group, another name for it could be carboxylic group because this is the carboxylic group. So decarboxylase refers to the removal of a carboxylic group from an atom. All right. So we now have putrescine. Putrescine is this structure that does have 2 amino groups. 2 amino groups, we're going to add a methyl to one of them to form a structure that's called N-methylpyrrolinium. What's a methyl group? It's the CH3. If you just don't know, so you could refer to it as CH3 or you could refer to it as Me, whatever one you like. It's all the same. So N-methylpyrrolinium, we added a methyl to one of the nitrogens in the putrescine by using an enzyme that's abbreviated as SAM. SAM stands for S-adenosylmethionine. Right? Just say SAM. Just say SAM. You don't have to say S-adenosylmethionine every single time. So from N-methylpyrrolinium that has a methyl on the nitrogen, we want to transfer it to N-Methylpyrrolinium Cation. A cation is a structure that has a positive charge on it. And the positive charge here is found on the nitrogen. You could ask yourself why there is a positive charge on the nitrogen. That's a very good question. Nitrogen, in general, when you talk about it, could bound to other atoms by only 3 bonds. That's naturally, all right? But it does also have a lone pair. If you don't know what's a lone pair, it's 2 pair of electrons that are found on the atom but they don't form bonds. They're just found on the atom itself. So actually, the total number of electrons that are found around the nitrogen are 8 bonds. 6 of them are in the form of bonds with another atoms, and 2 of them are just for the nitrogen without sharing with another molecules or another atoms, in the form of a lone pair. Sometimes you could find the nitrogen attached with 4 bonds. 1, 2, 3, 4. How is that possible? It's possible because there are sometimes that this lone pair actually could move to form a 4th bond. But these 4 bonds are not the natural state of nitrogen. The natural state of nitrogen is only being bound with 3 bonds. So this makes a positive charge on the nitrogen. And this positive charge will help us to complete the reaction to make the Ecgonine molecule at the end that will help us make cocaine after that. So we have now the N-Methylpyrrolinium Cation that is on here. And then we're going to have something that's called enolate. What is enolate? Enolate is a form of compound that comes from something called acetyl-CoA. If you don't know what acetyl-CoA is some form of an intermediate that's found inside our body actually, and inside the body of plants as well. This is acetyl-CoA. If you want to form the enolate form of it, you're gonna basically you could just say that you remove the hydrogen in here and make the carbon have a negative charge. Why a negative charge? Because naturally the carbon does have 4 bonds that are attached to it. If we just throw carbon in here, carbon does have 4 bonds attached to it. So whenever you move a bond from it, which does happen sometimes, it's going to have a negative charge. Okay, just understand it that way for now. So this enolate form of the acetyl-CoA that has this negative charge on the carbon is actually a strong nucleophile. Nucleophile means that it's something that loves positive because it's electron rich. It's something that has lots of electrons on it. It's nucleophile. It loves something positive. What is positive in here? It's the N-Methylpyrrolinium Cation. Bingo! They're going to get attached to it very easily. So this is what happens in here by the help of this nucleophile and this electrophile. Electrophile means something that loves electrons. Electrons are negative. So what's the thing that's going to love the negative? The positive, which is the N-Methylpyrrolinium Cation. And what is the thing that's going to love the positive? It's the negative, which is the enolate one. So the electrophile loves the nucleophile, so they're going to react with each other. Let's just delete that. They're going to react with each other, forming this. This S is also the same as this L. It's something that explains the stereochemistry of the structure, so it's not really our main concern right now. We made this structure by the addition of this plus this, and then we added another acetyl-CoA, or to be more clear, another enolate form of the acetyl-CoA. All right. To make this structure. So this structure turned to this structure. How this structure turned to this very weird structure? Actually, it's the exact same structure, but it's the same idea as I mentioned to you in the L-glutamic acid. You know, substances are not really planar. They are not just found like that in a 2D dimensional way. No, they are 3-dimensional. They are 3-dimensional. So this structure is, this structure is this exact structure, but with the explanation of its spatial orientation, you know? This negative one, which is the enolate form of this carbon, is this carbon. What we've done actually is that we've bent this structure. We've bent this structure, and this actually is the same as the N-Methylpyrrolinium Cation that happened in here. This ring returned back to its form, this form, just to make it more clear. Alright, and this carbon returned back to its enolate form. Why did we do that? Because we've mentioned before that in order for this reaction to happen, in order for this acetyl-CoA to get attached to this N-Methylpyrrolinium cation ring, we need some certain conditions for this to happen. Something positive to be attached to something negative. This is what happened in here in order for this exact carbon to get attached to this carbon in order to form a bicyclic ring. We want this structure to close on each other, on themselves, to form a bicyclic structure. Bicyclic means they are two cycles, two rings. They're going to close on each other to form this structure. Alright, so this is what happens. This enolate form is going to get attached in here, and when it gets attached in here, we're going to form the final structure. Yes, we forgot to go in here. We've mentioned putrescine, we've mentioned N-Methylpyrrolinium, and the final structure, which is the Ecgonine. Ecgonine is the tryptane skeleton that we mentioned when we explained what are tryptane alkaloids, which is this structure. The Ecgonine is the main skeleton of cocaine. Just by simple additions that we're gonna say right now on a clear board, you're gonna have cocaine. And now we're back with explaining the final structure of cocaine. It's a pretty cool structure. That's the Ecgonine structure. And actually, there's a modification to the Ecgonine structure to the other whiteboard that I made. Was a mistake. What the Ecgonine has attached in here is not a carbonine atom, it's a hydroxyl group, an OH, alright? And here we have COOCH3, or the methyl, as we mentioned in the other video. What is that? That is the Ecgonine, which is the main backbone of cocaine. What is cocaine? Cocaine is simply removing that, then adding to it a benzoyl group, acetyl-CoA, benzoyl acetyl-CoA to be more specific, so that we have this structure. Bingo. What is that? That is called cocaine. That's it. And that was the end of our video. I hope you enjoyed it, and thank you for watching.